This is an example that arose out of the quiz 3, which was held recently. Um, People were confused as to why this was a resonance case. So I thought we could do this as a worked example. It's a little bit different from some of the worked examples you've seen before because we have this function plus this function here as our driving term. So we could write g of t, the driving term, equals g1 of t plus g2 of t. Because these equations are linear, this can be broken into two different parts. So g1 is cos 2 omega t, g2 equals sine omega t, like this. All right. So what's going to happen is you're going to write the solution of this ODE as y equals, or y of t equals y homogeneous solution plus y particular solution. But that's going to be, the particular solution is going to include contributions from G1 and G2. So in this case, because this right-hand side is additive like this, we can write YH plus y particular part 1 of t, particular part 2 of t, right? And this particular part here is going to correspond to this driving term here, and it doesn't take much to see that this driving term is the problematic one because of the homogeneous solution. However, I'm just going to go through and solve this equation to demonstrate that this is a resonance case. So this, if you like, a summary of what I've just written down is how you can break this problem up and recognize that immediately that this is going to give you a resonance case. And then I think we'll just do the worked example for fun. So when we do these worked examples, we firstly solve the associated homogeneous problem. The associated homogeneous problem is this, where the driving term is set to 0. So we do our usual thing, sub e to the lambda t. We'll find lambda squared plus omega squared equals 0. This is our auxiliary or characteristic equation. We find that lambda equals plus or minus I times omega when we take the square root of that equation. And because we have complex conjugate roots, our general solution is this. Y homogeneous part equals, there's no real part of this, so we don't have an e to the something term out the front. We've just got cosine omega t plus, there's a constant in there, there's another constant in here, sine omega t. All right, so that's how we deduce the general solution of this equation. And what we've got to do now is deal with this particular part. So when we make guesses with our particular part, we would, our g of t is cos 2 omega t plus sine omega t, like this. Now this sine here, this part matches with this, right? And because it's additive, it will cause us problems. All right. So if it was multiplied, if we had cos times this, we wouldn't have the problem, right? Because it's linearly added, we're actually going to just get this as solving the homogeneous problem. This term does not solve the homogeneous problem. The frequencies are different. All right, so we've got a 2 cosine here, a cosine 2 omega here, but this sine omega is a problem. It's going to match with this term here. So what we're going to have to do is guess, from tables or whatever, a y particular equals. This is from this term here, right? That's the usual guess that you would make. Now you're going to have to guess t cos omega t plus t, C4 t sine omega t. Right, note that that's the same form of guess multiplied by t, right? So because you've got a resonance case, you multiply it by t, and you can get rid of this, or you can end up with a form like this. Note that it's all just added up, and we're now going to have to differentiate this thing and stick it into our equation. So differentiating yp is a bit of a nuisance because it's long and we've got some product rules to do. Differentiate the first function, leave the second function alone. Differentiate the second function, leave the first function alone. So that's okay. Then I've got okay. Now the second derivative. So that one's not too bad. These two terms here won't be too bad either. These two terms here need the product rule. So then I'm going to get Then my next, nope. The next one will be a minus C4 T omega squared sine. Alrighty, so that's a bit long and a bit unpleasant, but it is what it is. We can, by the looks of it, simplify it a little, because we've got these terms. I should have. Oh, have I got all of my terms? No, I think I'm missing one. Let's just go and count. So that one is that one. This one is this one. Right, so then I've got differentiate this one with respect to t. Then I've got to differentiate this one with respect, yep, so that's all there, that one's there. Then I've got, right, so I've got another term which is just plus C4 cos omega t from this one. I forgot to differentiate the first function, leave the second one alone. I just differentiated the second one, leave the first one alone. Okay, so that should now be the right number of terms. Yes. Okay, so be careful with long expressions like this. It's very easy to lose things. Let's simplify this a little bit. There's not much we can do about this. This one will simplify a little bit. We've got a bunch of terms that look like omega minus C3. We've got two of them. And we got two of these terms, C4 omega cos. Oh, hang on. Yep, so there's the other one. Then we've got the T ones. Then we've got omega squared T minus C3 cos omega T plus, oops, that's a minus. So I can bring the minus sign out the front. Get rid of that minus there. Plus C4 sine omega T. All right, so that's all the bits grouped together sort of as neatly as possible, these three terms. All right. So now what we have to do is substitute this into YP. Into dt omega squared YP equals cosine to omega t plus sine omega t, like so. Alrighty, so here we go. Okay, so that's just the second derivative. I've now got to deal with this plus omega squared yp term. So yp, you will remember, was c naught cosine 2 omega t plus c1 sine 2 omega t plus tc3 cos omega t plus tc4 sine omega t. Right, so that's this thing up here. Now this thing is equal to cos 2 omega t plus sine omega t. Okay, let's now look for some simplifications. And we're going to find the first bunch of them over here. This here, right? We note we've got a minus omega squared t times all of this. Here we've got a plus omega squared, and then we've got plus t in here. These terms all cancel, right? So the purple terms, purple highlight cancels. Alrighty, so we then have this term, and these terms here are going to add up. So we've got a minus 4 omega squared, all the sine things. Here we've got a plus omega squared, all the sine cos with the 2's, the 2 omega frequencies. So that's going to give us a minus 3 omega squared into c naught cos 2 omega t plus c1 sine 2 omega t. Then, so these terms join together. And then we're still left with this lot here, which we can't do anything with. Plus omega to minus 2c3 sine plus 2c4 cos t. But we know that this is now equal to cos 2 omega t plus sine omega t. Okay, now we can equate like terms. This cos 2 omega t has to match with this 2 cos omega t. There is no sine 2 omega t on the right-hand side of this equation. Therefore, C1 automatically must be 0. Similarly, this term here, this sine omega t term has got to match with this sine term here. There is no cos omega t term on this side. So we know automatically that C4 is also 0. That's the only way that these two terms can disappear on the left-hand side of the equation and match the fact that they don't appear on the right. So we now have minus 3 omega squared c naught cos 2 omega t equals cos 2 omega t. And minus 2c3 omega sine omega t equals sine omega t. This implies C naught equals 1 over minus 3 omega squared. C3 equals 1 over minus 2 omega. Okay, so we're almost at the end of our particular solution. We now have to back substitute, so our yp is equal to minus 1 over 3 omega squared cosine 2 omega t minus 1 over 2 omega t sine, cosine omega t. Right, so we look to see which term the C3 is associated with in our original guess. Just way up here, C3 is the t cosine term. So once we're all said and done, our overall solution y of t equals c cos omega t plus d sine omega t. That's the homogeneous part. Minus the particular part. And it's a resonance case because you've got this t cos term here. So I hope that's all correct. I hope I didn't make some sort of sign error. I think that's all. It all looks good. It all feels right. But obviously that's not the most pleasant calculation to have to work through. It is quite tedious, and you do have to be careful.